Welcome back, physics students, to video 6, components. In the last video we were looking at vectors. Now we're going to look at how we take those vectors apart and look at their components, or we use components. Now what do we mean by components? Well, basically we mean the vectors that we could add up to give us our resultant. In some cases we might know what the resultant is, and therefore we'd be interested in in this case, the horizontal and the vertical components of that vector. Now, what do we mean by that? Well, let's what colour have we got there? I can't see, blue. Let's go red, actually. Hopefully that's red. If we drew this vector here, again, okay, let's say that's R. That could be a force, for example. We should recognize that that force is made up of two components, one going that way and one going that way. Then when we add these two, so if we bring this vector across and do head to tail, like that, when we add them together, we would get this diagram here. Okay? So when they draw this vector here, it can just as easily have been drawn over here. That's what that diagram is trying to show. Okay? And so there's a little bit of maths. If we know the angle, this angle here, and we know R, we can work it out mathematically that the y component is R sine theta and the x component is R cos theta. And an example of that would be if we were given a displacement vector and we were asked for how far to the east they travelled or how far to the north they travelled. In this case, it's 500 metres at east, 40 degrees north. So how did they get this line to draw there? Well, that's east, and then they went up 40 degrees in the northerly direction. And so that's why that. Again, this arrow should really be drawn just there. In fact, let's fix that up. Okay? Just there. Okay, naughty textbook. And so, and because we're working out components which are vectors, they should actually have their arrows here as well. Okay? And so this would be the easterly amount and this would be the northerly amount. And being the components, if we added these two vectors together, we should get this. Now, in terms of components, what sort of things might we be asked? Well, again, it would be northerly, southerly. It might be horizontal component versus vertical component. It might be, what's another one? Horizontal versus vertical. They're the main one. Usually they're 90 degrees apart from each other. And so we're after the components that relate to that. Let's get rid of all that and bring this back. And so could you mathematically work out what the magnitude of this component and this component are? Okay, you can pause it and have a go if you're interested, or you can just keep listening and the answer will appear magically. There you go. And the maths isn't too hard, but if you are a bit swamped by that, or your maths, it's been a while since you did sine, cos and tan, make sure you ask and make sure that I can go through a couple of examples just how to work these out, because it's quite an important skill, being able to take a triangle and work out all the sides and things. Let's have a look at this one. This is, let's say this is a roller on a cricket pitch or a road or something, and you're pushing it, and you're pushing it downwards at this angle, so that angle puts a bit of extra weight on the roller on the ground to flatten it, but it also pushes the roller horizontally, because there's two components. There's the vertical and the horizontal component. The vertical component would add to the weight force of the roller because you're pushing down at it, and the horizontal component would be the component that would be causing it to roll along. Okay, and depending on what the resistance force is, whether or not it's rolling at a constant velocity or accelerating. Now, this triangle here is the triangle we would use to resolve it, but these vectors, if this is the center of mass, we could consider them to be acting like this, where, let's get this back, oops, I just drew on the screen, where this arrow represents the 150 newtons push, and this represents the horizontal component of that push, and this represents the vertical component of that. Okay, so we could replace this one vector with these two vectors and get exactly the same motion. Right, let's get rid of, what else do we need to get rid of? Get rid of everything? Not quite. Okay, let's try and get rid of that line. Erase all ink. There we go, otherwise that would appear on the next one. And there's our sine, cos and tan resolving it. So if you can identify this triangle and get everything in the right place, you'd recognise it's a right angle triangle, and that's why we often have our components at 90 degrees, because it gives us a 90-degree triangle, which we then can use sine, cos and tan. Another scenario where you'll be looking at components is on inclined planes, and we'll look at inclined planes again in another video, but this is just an example. So here you have a car on a slope, and it happens to be rolling down at a constant velocity. And basically what you've got is the weight force of the car is the predominant force, and all the other forces are resultants of that weight force, which is caused by gravity. And what you would identify is you'd have a force that's normal to the plane. Now what that means is this is the force that the car experiences, which is 90 degrees to the plane, or perpendicular to the plane. And we want to know that sometimes. You'd also have a component of the weight force which is a resultant of the friction or air resistance. Okay, now if the car is moving at a constant velocity or is stationary, that's a key point, so it could also be stationary, these three vectors here would add up to give you a triangle with no gaps in it, because all the forces are resolved. And this is what they're showing here, is the road friction. Now the road friction correlates to the weight force. The more weight you have, the more friction there is. But it's also a combination of the angle of the ramp as well. Okay, if this ramp was horizontal there, okay, the road friction component would be solely due to the road and no component due to the ramp. But as soon as you start tilting the plane, it gets a little bit more complicated, because you are getting a component of the weight force. Okay, and so if this force here is equal to this component here, and the normal reaction force is actually a response to the component of the weight force acting perpendicular to the plane. Alright, and so you can resolve that, and if you know this angle, you can resolve that, and we'll go through a couple of examples quickly now. In this case we have a car parked on a slope, but it's a rough road, starts to roll down the hill, oh no! After a short while it reaches a constant speed, so if you're chasing it, you might be able to catch up. It's 15 degrees to the horizontal, the speed is slow, so the air resistance is effectively insignificant. Determine the magnitude of the friction, road friction on the car whilst it is rolling at a constant speed. There's all our information. There's our diagram. So that's our 15 degrees there. There's our weight force, which is the first force we would identify. And we would recognise that the normal reaction force has its component of the weight force there, perpendicular to the plane. And we would have a magnitude of the road friction, which is a component of the weight force. And the 15 degrees, if you do a little bit of geometry, you should be able to work out that that 15 degrees goes there. And if you're not certain how we got that 15 degrees and the logical steps of how we do that, write yourself a little note, get me to show you how we got 15 degrees up to there. Because if you put that 15 degrees in the wrong place, you get the wrong triangle and you get the wrong numbers. So you need to make sure that you understand how it is happening. And then it's a simple matter of maths. Now in this case the car is travelling at constant velocity, and so the road friction is balanced by all the other forces, and so it's not accelerating. Now, what would it look like if it was accelerating? Well, you would have to have a component out here that would be causing the car to accelerate. And so effectively, the friction force would be less than the component of the weight force acting down the ramp. And so you'd have a little bit left of the weight force acting parallel to the ramp that would cause the car to accelerate. And that's what happens when you start tilting or increasing this angle. More and more of the weight force, which is provided by gravity, increases and causes it to accelerate. So this is the logic of the working out though. So your net force is 0 because it's constant speed, no acceleration. And so your weight force perpendicular is equal to the normal force perpendicular. So that's that one there. Your force due to friction is equal to the weight force that is parallel, or the component of the weight force that is parallel to the ramp, which is that one there. Okay, and so F friction equals F weight sine 15. So they're working out this one here, and you put the numbers in, and you get 4,000 newtons. All right. Let's do another one. This time it's a skier going down a slope, and very similar diagram. Again, constant velocity, and so that makes it a little bit simpler. We will be doing some questions where it's accelerating, and therefore you've got to factor in your acceleration force. Sometimes you're working out the rate of acceleration, sometimes you're working out the resistance force, but basically there's a disparity between the weight force parallel and the friction force, and so it's a little bit of maths. And again, very similar working out. What are they working out? The normal force here. So you're actually working out this component first, and then saying, well, this is a reaction to that weight force, and therefore it's equal but opposite, and that's why it's 660 newtons. Then the sum of the resistance forces is working out this vector, which is in response to the weight force. So that's a reaction force. And so if you work out this component, you work out that component. And that's what 177 newtons. Now, relative motion, we just quickly need to talk about. This is more important when you start doing relativity, but it's also a situation that you encounter just looking at questions. So when we talk about motion, generally we are viewing a situation as an observer outside of the situation, but occasionally you might get a question where the observer is within the situation. So in this case, the observer is in this car, which is travelling at 90 kilometres an hour. And so this car, which is travelling 100 kilometres an hour, the relative velocity to the observer is only 10 kilometres an hour west. Okay, so that's what we mean by a relative motion. Again, and the same observer sitting in this car, but this time this other car is coming in the opposite direction, and so to the observer, the relative velocity is now 190 kilometres an hour due east. Now, 99% of the time, we're looking at as if we're an observer outside of the scenario, and so the velocities are relative to each other, and so we could work it out. But sometimes we get trickier questions. Hope that's clear. Alright, so the relative velocity of an object is the difference between the velocity of the object relative to the ground and the velocity of the frame of reference from which it is being measured relative to the ground, so the observer. In the next video, we'll look at forces and Newton's laws. Cheerio!